Hello everyone, and thank you for attending today's webinar, How to Optimize Your EBSD Results Using OIM Analysis 8. Before we begin, I'd like to cover a few housekeeping items. At the bottom of your audience console are several application widgets you can use. If you have any questions during the session, please click on the Q&A widget at the bottom and submit your question. We'll try to answer these during the webcast, but if a fuller answer is needed or we run out of time, you'll receive an answer later via email. We do capture all the questions. A copy of today's slide deck and some links to additional materials are available in the resource list widget that looks like a green folder. You can expand your slide area by clicking on the Maximize icon on the top right or by dragging the bottom right corner of the slide area. If you have any technical difficulty, please click on the Help widget. It has a question mark icon and covers common technical issues. Finally, an on-demand version of the webcast will be available shortly after the live session and can be accessed using the same audience link that was sent to you earlier. Now I'd like to introduce Matt Nowell, who is our presenter for today's webinar. Matt is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechSem Labs, TSL, when he graduated from the University of Utah in 1995 with a degree in materials science and engineering. At TSL, he was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has been involved in a number of roles, including product management, business development, customer and technical support, engineering, and application support and development. In his spare time, Matt enjoys playing golf and pondering if the texture of his clubs will affect his final score. So now, over to you, Matt.
Well, thanks, Sue, for that nice introduction. I enjoy you giggling there at my final texture comment. Welcome, everyone, to the webinar, and thanks for attending. It's always tricky on a webinar, I think, because you're not quite sure who's going to attend. So when I thought about who might attend, I really targeted three groups. People who wanted to learn about OIM analysis in general, people who wanted to learn a little bit more about what OIM can do with their current work, and then people who might want to know what's new with OIM Analysis 8. So that's kind of the theme I went into organizing this webinar, and that's kind of where we'll go from today. Just for a quick review, if we do have some newcomers in the audience, I'll review EBSD, electron backscatter diffraction. This is an SEM-based characterization technique where we polish a sample, we put it in the SEM, we tilt it about 70 degrees, and we fire the electron beam into a grain. The electrons interact with the crystal, and we get a diffraction pattern that comes out that's detected by a low-light CCD camera and phosphorus screen. The idea with OIM, or orientation imaging microscopy, is that it's essentially automated EBSD mapping. So we couple the camera to the computer to the SEM. We define a measurement area and a step size, and we come up with a measurement grid. And at each point, we capture one of these diffraction patterns. We do some image analysis to determine the position of the diffraction bands. And from the position of the bands, we determine what the crystallographic phase and orientation is. And so we end up with a set of spatially specific orientation measurements, which we can then analyze in a variety of ways, which we'll discuss today. Now, with that introduction, I always like to talk about why crystal orientation is important. And it basically comes down to the term anisotropy. And so it's easy to understand that strength of a material can vary with direction. If you think of breaking a piece of wood, you can orient it with the grain to have a weak orientation. You can orient it against the grain of the wood to have a strong orientation. This same concept or principle applies to materials on a crystallographic scale, where certain orientations will have a strong property or a strong orientation. Certain orientations have a weak orientation. So material scientists can think about changing the properties of material by controlling this orientation and anisotropy. And so if you're going to try to do that, you also need to be able to measure the orientation, and that's where EBSD really fits into the picture. Now, I always laugh because when I learned this, you basically said, well, we're not going to worry about that, and we'll average it all out, and we'll call everything isotropic and throw in a safety factor. It's really not true, though. Most material processing, whether you're depositing a thin film or deforming a piece of metal, will create some amount of preferred orientation. And so being able to measure that and take advantage of that is a pathway for pushing material performance a little bit further. And EBSD is really an ideal technique for measuring this texture, orientation, and grain structure to understand how this structure influences performance and properties. So OIM is really a link in this whole microstructure processing properties relationship. And so the better we can characterize the microstructure, the better we can understand the link between how we process and material and the resultant mechanical properties that come out of it. And so that's kind of the quick idea of where we're going. So with OIM analysis, often when we look at an EBSD system, especially in a commercial evaluation perspective, there's a lot of focus on the detectors and data acquisition and pattern indexing and what have you. Really, in the big picture, collecting the data is just the first step in the process. And so OIM analysis is the tool that's used once you have this data for visualizing, measuring, describing, and quantifying the measured microstructure. And as you can see here in this little chart, we're able to get out maps, charts, plots, and textures from this analysis. So with that, we'll go to our first little quiz. We put a few quizzes in here, and what we want to know here is, have you ever used OIM analysis before? I'll wait a few seconds. Go ahead and click yes or no and click the submit button. Click ahead. So we can see that. So it looks like we have about 2/3 who have used it and a third who are new to this. So I think that hopefully the introduction part will be very useful. So the first thing we generally get with OIM analysis, and probably one of the things that has driven the acceptance of the technique, are the maps. So first of all, they're very colorful, they're very pretty, but they're also very meaningful and give a lot of information about the material microstructure. When we create these maps, there are lots of different options. We can do grayscale maps where we're shading black to white. We can do color maps. We can combine them. And then for any of these different map types, we can add on a variety of different types of misorientations, grain boundary, phase boundaries, special boundaries that give a picture of a view of the microstructure. In addition to these maps, we can also create charts that show the numerical distribution of these measurements. And so that makes it easy to see, average grain size, misorientation distributions. We can get statistical information that makes for easy comparisons. And we can represent it in a graphical means with a picture, and those two pieces fit together nicely to really describe the measured components of the microstructure. From an orientation point of view, the other thing we're able to show is the orientations in what we call plots. And these are for measuring, for visualizing orientations and misorientations with things like pole figures or inverse pole figures or Euler space plots. That we can show either as a discrete plot, or we can actually figure out what we call a contour or a density plot to get an idea of how strong a texture is. That's usually one of the questions we want to answer with EBSD is our orient distribution close to random, or is it not random? Is it a preferred orientation? And that's where the OIM analysis plots play a role. So there are lots of different types of outputs we can get from OIM analysis. The challenge then becomes, how do we make this accessible and organized? And so one of the features I wanted to talk about is what we call our QuickGen Toolbar. This is really a good starting point to access the most commonly used maps, charts, and plots. It's also customizable to set up your own preferences and to do full sort of one-button analysis. And this is available just as a toolbar in the OIM analysis user interface. The outputs that are available are the most commonly used EBSD outputs. So the first one is the orientation map. The orientation map is probably the most common EBSD map, and it just shows what's the orientation each point colored by orientation. So generally you see this with a colored inverse pole figure that we see there in the bottom of the figure. So here, any point that's shaded blue is near the 111 orientation. Any point that's shaded red is near the 001 orientation. So this map allows us to quickly see both the orientation, the grain information, and any preferred orientation. If your map is all blue, it's going to have a preferred 111 orientation. This next example is why I think it's really important to show this and the importance of that spatial resolved orientation measurements. This is an example from an aluminum extrusion where the owner of this piece had problems with manufacturing issues, and they couldn't figure out what was the difference between these two different areas. And so they had looked at grain size, and the grain size was about the same. They had looked at orientation with XRD, and they were about the same. And they said, we can't see a difference. So we said, well, let's take a look with EBSD, and we collect our EBSD maps, and we see them here. And you can see that both maps have about the same amount of fraction of red and blue, or 100 and 111 components, but they are very differently spatially distributed. There are much more larger clusters in the center, much more randomly smaller clusters on towards the edge. And this is something you just wouldn't see with a different characterization technique. And so this is where EBSD fits in between XRD, which sort of averages all that orientation information together, or TEM, where you'd go in on a grain by grain, nanometer type scale. EBSD fits in very nicely for this type of characterization. The next output on the QuickGen Bar is the image quality map. This is another very popular map we see where the brightness and sharpness of the diffraction pattern is translated into the contrast of the image quality map. So this generally shows very nice grain and grain boundary contrast. And this is an example from a titanium alloy. You can see the last within some of the grains. You can see the grain boundaries. You can sometimes see plastic strain. You can see phase contrast. So you can get quite a bit of information from an image quality map that looks a lot like a micrograph, a traditional metallographic micrograph. The third QuickGen output is the grain map. With EBSD, because we're measuring discrete orientations, we have to group those together with some algorithm to determine what the grain size or grain structure is. So once we've determined what these grains are, we then can randomly color these to show the size, shape, and morphology. When we're doing this, we can also exclude certain boundary types, for example, twins, from the grain calculation to get an idea if the grain size is different with or without twins, because twins may behave differently than random boundaries in a material. So this is just an example from a CAD-TEL solar cell with and without twins. In addition to when we do this, the real trick with this is you have to determine what the tolerance angle you want to use is. And so EBSD is a great tool for trying to figure out exactly what a grain and grain distribution is for a given material. Deformed microstructure may form subcells. You may tweak these grain tolerance angles to find what those subcells values are and then what the larger grain size values are. And as you adjust that grain tolerance angle, you can get the corresponding grain map, which shows that grain structure. So you get a very nice correlation back with the image quality map. And then, of course, we can get the grain size distribution. So we can get the average grain size, the standard deviation, some statistics of that. And really the reason that's important is this is a quote from a paper a few years ago in Materials Today, where it says, it is now well known that the grain size is the major microstructural parameter in dictating the properties of polycrystalline material. And so that's your Hall-Petch equation there on the left. On the right is a steady state strain rate equation, and both of those are a function of the grain size. So by measuring the grain size easily, reliably, and quantitatively, we're able to better understand how a material will perform in different mechanical response situations. The next type of map is what we call a grain boundary map, where we can color different boundaries. In this example, the low angle boundaries are red, mid angle boundaries are green, and high angle boundaries are blue. And we overlay that on an image quality map. You can always adjust what the colors and the boundary types are for this type of a map, but you're able to see where boundaries are located. For example, in here we see twins pop out in this nickel superalloy, and then we're able to identify if they're a special grain boundary type. We can correlate that also with the misorientation angle distribution. This gives an idea if any preferred grain boundaries have developed. We can compare this to a random distribution. So in this case, we see there's a big, strong peak there at 60 degrees, which would be a twin boundary, and there's a little peak down at the end, which indicates some amount of plastic deformation in the material. While we've done the EBSD, we also identify what the phase is, so we can plot out a phase map. And if you've collected the information simultaneously, we generally get EDS chemical information as well. So this is just an example where we have 4 different element maps from the same area that were collected simultaneously. And in a little bit, we'll talk about how we can use that information for better phase analysis. And finally, with the QuickGen, we can also get pole figures and inverse pole figures for the material. So that QuickGen bar gives a nice, quick overview of a lot of aspects of the microstructure. We can, of course, start to think about customizing this. So this is just an example where we take the image quality map, we add a color map of an orientation, we add them together to get a combined map. You can select different map types for each one of those, and basically customize your output to communicate the information that you think is important for your material. So once we have that, we get to the idea of there's lots of information. So when you start looking at the different combinations, you can get lots of different outputs. So to me, the next question comes out to be, how can we effectively organize and use this information? And so I'm going to talk about templates, and I'm going to talk about what I've just termed packages. So the first important concept are what we call OIM analysis templates. So once you've customized a map or a set of maps or a plot or a chart or whatever you can do, you can save all those details into what we call a template file. And then you're able to use that file to apply to another data set, another sample. You can share it with a colleague. And they're able to repeat this analysis. So whatever you've selected for your boundary ranges, your colors, your tolerances are all then consistently shared across that template. So I think it's an easy use for repetitive customized analysis of your OIM data. And these templates can also be loaded onto your QuickGen Toolbar. The other thing we've tried to do is take different sets of analysis and group them together into different packages. So one is advanced grain analysis. This is where we can look at the grain size, grain shape, grain properties, ellipticity, circularity, different metrics of what the grain looks like. Advanced boundary analysis. This is where we take out different types of boundaries to look at misorientations, grain boundaries, intergrain misorientations, twin boundaries, phase boundaries, reconstructed boundaries, and reconstructed twins. Advanced material properties. So how will a material respond to different loads? This is just an example of taking a piece of tantalum. If we squish it together, how will the material deform? We know what the slip systems are, so we can see where different parts of deformation will occur. So we can look at this in terms of Taylor factors, Schmidt factors, elastic modulus, and dislocation density measurements. And then, of course, we can go to the advanced texture analysis. So we can do that full calculation of the orientation distribution function, or ODF, to determine how strong a preferred orientation is. And that's just important because if we look at this, this pole figure here, each point in a pole figure could correspond to one measurement or could have 100 measurements all of the same orientation. It's hard to tell how many occur in a single discrete plot, but when we figure out this ODF and plot it as a density plot, we get a measure of how strong a texture is that makes it more easily comparable with other textures. We also have what we call advanced data manipulation. And so for this is just one example. This is a large area aluminum friction stir weld. You can see the 1 centimeter scale mark there. And so how can you analyze such a large area with different orientation components? You can see the base metal on each side. You can see kind of the swirl of the weld. You can see this onion ring layer structure in there. So one way we can do this is through data cropping. So we have functions for cropping, for merging, rotating of all this manipulation. But data cropping, we can go in and pick out different subsets of the region and then pull out pole figures from those different regions. So we see on the right the base metal. In the middle, we see part of the weld, and we can kind of see how that's oriented relative to the normal of those onion ring layers. And then in the recrystallized nugget, we get a different texture. So all these different outputs are important because we can start to think about how different ways of processing a material can change the microstructure and how we can measure it. So this is just an example of using EBSD to characterize deformation. In this case, we're going to talk about plastic or permanent deformation, where whatever load we apply is going to cause a permanent change in the microstructure. These changes correspond to misorientations, which we can measure. And so this just shows taking a piece of brass and rolling it to different reduction levels. So we're going to basically 5, 10, 20, and 30% reduction. At 5%, there's only a little amount of deformation. As we add more and more, you can see that within a grain, the color is not as constant. It kind of rotates around a little bit as the material deforms in response to the load. So with EBSD, we can get an idea of the amount of deformation present in a material to understand what may have happened prior to analysis. We can also try to understand how a material will perform based on our microstructural characterization. And so this is an example that I like. So I took 3 different materials, and I'd measured the microstructure before and after, and then I used an indenter in there just to see how it would respond to a mechanical load. And so the first material was Inconel 600, about 15 micron grains. We got an indent that was about 150 microns. Then took Inconel 718, where the grain size was about a factor of 3 smaller, about 4.5 micron grains. And so if we go back to that Hall-Petch equation, smaller grains means it should be a little bit stronger, more resistant to deformation. And as we can see, the load there does produce a smaller sized indent. And then went to a 304 stainless, where the grains were much smaller. These are 2 micron grains. You can see in that color scale, it's much warmer than the blue area. That's a orientation deviation type plot. So it says there's some work hardening already present in the material. So it's more resistant to the deformation, and the indent's only about 120 microns. So it was easy to kind of say, yeah, we could see how the microstructure would dictate how the mechanical response would be with an indenter. This was just a cool example in my mind, because this actually came from my son. So they implant this little clip in pediatric surgery. And so it's a titanium clip, and of course, as you take this and as you bend it, the bend puts the material under different loads. So you're going to get an area of compression and an area of tension. And so I was just curious to say what's the microstructural changes, and it's also, again, over a large area. So this is a millimeter scale type of a response. But if we look at these different areas, so the bent region here is shown on the top, the straight region's on the bottom. The bottom, we can see nice sort of equiaxed grains, a lot of blue on the map on the right where there's not a lot of deformation. When we deform the material, this is titanium, you can see we start getting a lot of these linear shaped features. That's some deformation twinning that occurs. And we can see the plastic deformation that occurs sort of on both ends of the bend where we're in those different stress states. And then this is just an example from a partially recrystallized steel. When you take something deformed and you heat it up, it'll form recrystallized strain-free grains. And so with EBSD, we can take something sort of in the process and look at it, and we can see how much of this recrystallization has occurred to get an idea of how fast the recrystallization rate is. So this is just an example where if we look at the local orientation spread map on the right, the recrystallized grains show up in blue. The deformed areas show up as the warmer orange and red colors. And that allows us to customize heat treating times and temperatures for optimal, recrystallization behavior in the least amount of time and at the correct temperature. So those are some examples of how these measurements can correspond to real life. Flipping back to OIM analysis, again, we get a lot of data. So one of the things we have in the software is what we call our project tree. And it's a way, sort of intuitive way to manage this data for sort of all user levels. Within each level, we're able to see the data set, different what we call partitions. So if it's all the data, high confidence data, if it's a specific phase or large grain only in this example, we're able to see that data organization. We can go into each one of these and import or export and rotate or clean up. You can copy and paste from one area to the other, and you can save all this data and analysis together in what we call a project that's portable from one machine to the other. And so it's a nice way of organizing this large amount of data that's possible. Another concept with OIM analysis that's very useful is what we call partitioning, where we can take our entire data set and break it into microstructural subsets so that we can characterize each portion separately. We can do this point by point or by grain-based properties. We can use logic to build bigger partition definitions, and we can save these definitions as a template for future use. So in this example, going back to that steel example, we've taken out and partitioned the recrystallized area from the deformed area. And so what we're able to do then is say, well, what's the grain size of the recrystallized area? What's the grain size of the deformed area? What are the textures? You can get an idea of how each component might influence mechanical properties as sort of a composite type of a material within the microstructure. We can also interrogate the data interactively. And so this is an example from a stress corrosion crack going through a piece of pipeline steel. We can see that image there on the left, the crack going through the material. So we can go in and manually click across that crack and figure out what the misorientations that the crack propagates through. We see the crack path misorientation is shown on the distribution on the right in blue. The total microstructure is shown in red. And you can see that the blue crack path goes through a lot of different types of misorientation. So the crack's going through preferred grain boundary types and generally trying to avoid some of the twin boundaries present in the material. So you'll see a lot of research work of people trying to introduce more twins through grain boundary engineering to help improve crack resistance. And this interactive analysis is pretty comprehensive. Again, we can do things by points, by grains, and by orientations. We can do point-to-point misorientations. We can do a vector showing point-to-point and point-to-origin misorientations. We can visualize the unit cell. We can visualize the crystal plane geometry. And this can all be saved and exported for further analysis as well. And then we can also highlight different subsets. So if we look in this case for a grain size distribution, I can apply a color to that distribution and then see how those colors correspond to the map there. So the largest grains are red, the smallest grains are blue. And we can do that basically between any two outputs in the software. And then just as a conceptual idea, this is just an example from an in situ deformation experiment. So we deformed a material and we took OIM maps along different places along the curve here. And so we end up with multiple data sets. And the idea is, how can we analyze this data efficiently? That leads the idea to a batch processor. So this is an example from a heating stage where we've gone from 850, 900, 920, and then back down. And we see the phase transformation from ferrite, which is BCC, to austenite, which is FCC, and then back down again as it goes through this temperature reversal. Using the batch processor, we're able to do this type of analysis pretty easily because we can specify what we want to happen for each data set and repeat it for all the other data sets. And so what you're able to do here is you can do different cleanups, different rotations, apply different map templates, and use this for all the different map sets. So, it's not uncommon to do 200-300 different maps together with this batch processor. And it's just available as a tool on the OIM Analysis Toolbar. I just said that. Now, of course, once we have all this data, it's quite possible, to say, how do we start to manage all these different data sets and how do I keep track of it? One of the tools available in OIM Analysis is what we call the data miner, where it will index your hard drive or multiple hard drives or portable drives to figure out what data sets are present on your system, and we'll give you this list where you can see data sets with step size, number of phases, number of points, what EDS elements are present, the average confidence index. You can go in here to open the files, you can delete the files, you can find duplicates, and you can archive multiple drives. So if you're going back and saying, hey, I want to go find that steel sample I looked at, it's pretty easy to go in and find this within OIM Analysis and start working on it. If you work in a lab that has lots of different materials coming through or lots of different samples, it may be a tool that's useful. And then if you want to take lots of data sets to the next logical extreme, it's the idea of doing what we call 3D EBSD or 3D EBSD and EDS, where we take a EBSD map, remove some layer of material by different means. It can be through focused ion beam, it can be through broad ion beam, it can be through mechanical polishing, and take another OIM map and then stack them together as a three-dimensional volume. So these are just two examples of a volume. One's a meteorite there on the left. On the right is an aluminum alloy. And so this 3D visualization is also built in as functionality into OIM, where we can visualize, the orientation, image quality, phase, EDS, and local orientation as 3D volumes. We can calculate the grains in 3 dimensions, grain size, grain average orientation, and grain orientation spread. You can show different levels of transparency to see things within this volume, and you can interact again and pick out specific grains for analysis with this 3D type of an approach. So for our next quiz here, this is kind of an overview of what's currently in the software. If any of these think they'd be useful for your work, I'd be interested in knowing. So if you don't mind just kind of clicking across there and then submitting, I'll wait for a few seconds. Quick drink too. Just kind of wanted to use this as a baseline for the current software. Okay, we'll go ahead here. Try to comment on the fly on anything, but thank you for your feedback. And with that, we'll shift gears to the second part of the webinar, which is what's new in OIM Analysis 8. This is a product we announced at M&M, I think it's still last month. It may have been a little bit more than a month. It might have been in late July. This is a product we aim to start shipping here in Q4 of this year. So my guess is probably going to be November is when it will start shipping from the factory. But it's kind of the next step in evolution of this OIM analysis product. This is a product that has kind of been our flagship for analysis, and we've added a lot of new features, and that's why we've gone from 7.3 to 8, as we think there's a lot of very good, useful new features that will open up some new areas of analysis. So the first one, we always start with the easy one, is Windows 10 compatibility. Basically, it helps it make it compatible with new computers you buy. Not a lot to say about that other than it is compatible. But more importantly, it is, the term I've used here is multi-threaded. And what that allows us to do is take advantage of the modern computers with multi-core CPUs. Prior to OIM 8, it was a single-threaded application. So, you'd go buy a new computer and it'd have 8 cores, but each core was slower than your old computer. So OIM would actually end up being slower with a newer computer, which could obviously be a little bit frustrating. With the new computers and new multi-threading and multi-core performance, your performance basically scales with the number of available cores. So for better or worse, the more power you can throw at it via computing hardware, the faster it can be. And that's really important because we haven't talked a lot about data acquisition, but cameras have gotten faster. SEMs can put out more beam current. You can get more data in the same amount of time. Now OIM Analysis is able to help process that more efficiently. So we thought that was an important step. Probably the biggest feature we've introduced is EBSD pattern indexing within OIM Analysis. So what we're able to do is we can re-index points, data, partitions, whatever we want to do within OIM analysis. We don't have to do our re-scanning within the acquisition software anymore. And so we can do this reindexing, either use the band positions saved via Huff peak information, or we can save the EBSD patterns. And so the reason that differentiation is important is that, Huff peaks are easy. They're generally saved by default, and they generally reindex fine unless you're not finding the bands correctly. So if you save the patterns, then you can go in and adjust things like your Huff transform parameters. You can adjust some of the background stuff you're doing. And so once you do this, you can start talking about reindexing. And again, we can go into do a real single point. We can do the whole data set. But one of the neat ideas is you can go in and say, I can only reindex a partition. So, for example, if we go and define and say, show me all the points that have a low confidence index, those could be the points we target for reindexing. So no longer do you have to reindex everything. If 95% of your data is good to begin with, you can target your reindexing efforts only on that 5% that needs improvement and not have to do the other 95% again. As part of the reindexing, we've also implemented our Kaiscan and MPAR functionality, which I'll discuss. And we've also built it to be able to do batch reindexing. So if you are doing 3D work or in situ work, you can reanalyze multiple data sets as a set. I mean, it doesn't have to be 3D or in situ. You can just do a set of multiple data sets. But if you want to do reindexing, you can do it as a batch job. So this is just a little example here. So we've clicked on a point. It brings up the pattern. We can index it. It's the same triplet indexing engine that we've used for the initial data collection. But with this, we can come in and we can adjust the phases we're using, the band detection parameters, the calibration values if necessary. We can also optimize image processing. So we can create a brand new background. We can create a background from all the patterns or just a pattern in a partition and apply additional processing. So this can be really important if you have multi-phase materials with different pattern qualities or signal intensities, as now you can adjust your background correction so that your band detection improves for each individual phase. And it also lends itself well to what we call Kaiscan. And Kaiscan is the idea of using simultaneously collected EDS information to improve our EBSD phase differentiation. And it helps us to improve the differentiation of crystallographically similar phases. So this is just an example here of a phase map from an aluminum silicon casting alloy. These two structures are both face-centered cubic, similar lattice parameters. So the before Kaiscan phase map there is very noisy. But if we use the chemical information to tell us which phase is which, after Kaiscan, it shows a nice representative phase map. So I wanted to talk a little bit more about in detail about why this happens and why it's important. This is an example from an inclusion in an aerospace titanium alloy. So these inclusions you can see on the phase map in the bottom left there, they should all be yellow. They should be alumina particles. We know that from the EDS, but their indexing is blue. It's the titanium matrix. And so, when we first started looking at this, it was the question of why is that the case and what can we do? So the first thing we looked at is to say, let's go to this orientation and look at it. So if we pull this pattern out, which is the one on the top left, we can see the pattern. So the pattern quality is not an issue. We're getting nice sharp patterns. But basically the geometrical arrangement of the bands, which correlate to the planes, are similar between alumina and titanium. And you can see that from the indexing overlays for alumina and titanium on the top there, especially on that strong pull in the top right area of the phosphor screen, but even the different triangles it forms, there's a lot of the planes that have similar positions. So when we find those bands, they index with both phases reasonably well. And so this is an example on very good patterns. When we bin the patterns and run them faster as we would for a traditional map, you can see how the pattern quality changes, why that would still be an issue. So we can look at it from a theoretical point of view and say, hey, there are certain orientations that will index well, and there are certain orientations that will give us problems. We can figure out where those are at. We see that with that plot on the bottom center of this chart here. where the red areas are easily indexed, the blue areas are going to lead to ambiguous indexing. And it's just because you can have high symmetry poles with similar interplanar angles in the same position. It's just going to cause a problem. And we just found this one serendipitously. But what we can do is to say we know that EBSD works well when the crystal structures are different, and we've seen EBSD doesn't work well when the crystal structures are similar or they produce similar looking structures. And so how do we overcome this? Well, the easy answer is we use our chemistry. We use our simultaneously collected information, because it's going to tell us, what phase information, what corollary phase information will differentiate things better than the EBSD will alone. So the idea of combining EDS and EBSD isn't really new. We've actually been doing it for about 20 years. It's just a little example that was collected showing nickel counts in a superalloy. But the idea of putting it together and calling it Kaiscan is something we introduced, and then we brought over into OIM Analysis with OIM Analysis 8. You can see now when we apply Kaiscan, those precipitates are now very well resolved within the titanium matrix. We can also resolve there's some zirconium oxides and some erbium oxides that are present. So we're able to differentiate the different phases much easier. And now by doing it within OIM Analysis, we can go and target those chemical phases much more easily than we could previously. And then with Kaiscan, just to give an idea, we put some features in here to help with the spatial resolution. So these are some submicron particles of a nickel film on an iron substrate. The step size is about 30 nanometers, but we're still able to go in and say, let's use that chemical information. We can shift the spatial position of the EDS signal due to interaction volume changes to better match the EBSD signal. We can do some averaging that allows us to go in and say, let's build a good phase map even with submicron scale precision. And it still allows us to use EBSD in the cases where there's polymorph. So when the chemical signature is the same, but the crystallographic structure is different, we can still say, great, for that chemical fingerprint, we'll use EBSD to distinguish different phases. So this is just an example from an aluminum silicate where you'd have 3 different phases that are present. And so here's an example where we use EBSD alone on the top left. You can see kind of noise areas, EDS alone on the bottom left. And then when we combine the two, we get very accurate characterization of all 9 phases in this particular material. So we're able to take areas where EDS works well, areas where EBSD works well, and use that to put the most accurate and correct picture for all the phases present. Now, I mentioned earlier, camera speeds are improving, but as cameras get faster and faster, if you don't put enough beam current in, it's also possible to get noisier and noisier. That decreases our signal-to-noise level. And so noisy patterns can lead to noisy scans, which obviously we don't want our indexing rate to go down just to say we went faster. But as we thought about it, as we tried to say, what can we do to improve this without necessarily slowing down the system? And that led us to the idea of what we call NPAR, or neighbor pattern averaging and reindexing. This is where we take a set of patterns and we average each pattern with all the neighbors around it. So we generally collect our data on a hexagonal grid. So each point will have 6 surrounding neighbors. So if we average each point with its 6 neighbors, we get a pattern with a better signal-to-noise ratio through this spatial averaging. And so this allows us for a faster collection at lower beam currents. It's good for things like insulating materials. And it's nice when you want to push the performance of your system without having to increase beam current. And so this is just an example for this chart on the bottom right here. As we increase the noise, generally indexing drops off. But when we apply this NPAR, that blue line stays about constant. We can keep indexing performance working well applying this type of a filter. This is just an example. Without NPAR, we get about 11% success. With NPAR, it jumps up to 96, getting the true microstructure. So we looked at this sort of systematically to figure out where things are going. So, you know, obviously if we get a good image as we see on the top there, it's pretty good. But as we introduce more noise, we're still able to get out the correct microstructure. So we feel like we're not introducing artifacts through this approach. And so this allows us to do some interesting things. This is showing going at 100 patterns per second at 100 picoamps. And so without it, we're doing about 40% indexing. With it, we jump up to about 96, 97%. You can see most of the black points remaining on the right there actually occur near grain boundaries. That's about what you'd expect because that's where the pattern averaging won't average as many of the same patterns. We'll get two different overlaps, and so we don't expect as much improvement near the boundaries. And this is a similar map saying we can go 500 points per second at 500 picoamps. Again, 22% up to about 96%. But we also see advantages on different type of materials. So this is a rolled aluminum sample. So aluminum's a lighter atomic number. It has a little bit less signal to begin with. But we can still collect here. This is 1,000 points per second with about 4 nanoamps beam current. Traditionally, we're only getting about 72% indexing. When we apply the NPAR filter, it jumps up to about 95%. And then this just kind of shows how different materials will perform differently. So this chart on the right shows for a dual-phase titanium, a rolled aluminum, and a polysilicon sample, and a yttrium-stabilized zirconia. You know, for any sample, if you put in enough noise, eventually indexing falls off. But by applying NPAR, there's room for improvement on all different types of samples because it's a signal-to-noise problem. And this is just an example from a non-conductive ceramic sample. So we run it under traditional conditions, say 20 kV, 5 nanoamps, a lot of charging, drifting problems. We run it at 12 kV with 1.5 nanoamps beam current and apply NPAR. It looks perfectly fine. The other thing we've put into OIM analysis, what we call Prius. Prius is our microstructural imaging approach where we use the phosphor screen as an electron detector. We can do this now in analysis where we look at channels or we look at saved patterns. It allows us to do a few tricks. So to get an idea what Prius can show, this shows from a corroded steel sample, one of the detector channels, the bottom channel, shows topographical contrast. The center channel shows orientation contrast. And the top channel shows atomic number contrast. This is another example. This is from a thermal barrier coating on a turbine blade. Again, the top shows atomic number contrast. The middle shows orientation contrast. The bottom shows topographical contrast. So this is sort of a common way of splitting out contrast mechanisms. So within analysis, we now have 3 standard channels that allow these to be displayed. And so we're at the point now we generally look at Prius maps on every sample. So this just shows 4 different samples looking at the 3 standard channels of what contrasts are available and the different types of information we get out. So the vertical columns here are all from the same sample, or the vertical columns here are all from the different channels. The horizontal are from different samples. And we can see we get different information from the different detectors, but we get this automatically during the regular data collection. And then if we've saved the patterns, we can also do some manipulation within OIM analysis. This shows those 3 channels on a foil sample, so we see orientation contrast, but we also see topography. And so if we can isolate that out to just get rid of the topography and only show the orientation contrast. So here, this just shows where we're going to do that. We're going to define a detector region of interest as a thin vertical line through the pattern, create an image only using that channel, and then you see we've suppressed the topographical information and we only show orientation contrast. So that's the type of analysis we can do in OIM analysis with the saved patterns. The other advantage of Prius is that because it's using the phosphor screen, we can do this at high temperatures in situ experiments. This just shows the Prius images when we approach 1,000 degrees C. The fluoroscatter detector diodes don't work well at these higher temperatures, but we get good Prius information, which gives us a quick view of the microstructure relative to a full orientation map. Other features that are available now in OIM Analysis 8, one is correlative microscopy. And so what that allows us to do is import other spatially specific measurements for visualization and correlation with the EBSD data. So you can imagine we've talked about doing it with WDS, AFM, CL, nano indentation, anything where we have data on a spatial grid. We can then bring this in, we can match up the data, and we can tie it in as an additional OIM analysis channel. So this is just an example where you can see we brought in a channel and we're now overlaying it on the bottom with our EBSD data. So we can see how these other characterization techniques combine and complement the microstructural data we get with EBSD. We can do what we call correlative plots. So this is where we can use two different measurements on two axes of a plot. So this is an example where we've looked at the dislocation density versus the average Taylor factor of a material. It just helps us get a better understanding of how different EBSD measurement metrics may correlate with each other. And so some are pretty easy to understand. You could do image quality and confidence index. You know, as confidence index or as image quality goes down, we'd expect confidence index to go down. But, you know, like this one, trying to understand how Taylor factor would affect GND density certainly wasn't exactly what I expected. So we can get some new ideas from looking at these type of plots. Anti-grain analysis. I mentioned before when we looked at grain size calculations, we grouped together points with orientations as the same grain. So what anti-grains do is say, look, what points are left over? Can we group those together that even though they may not have the same orientation, they're still spatially correlated? So if you get 10 points together that all don't index, that may indicate something, and we've called that an anti-grain. We've seen that can be correlated with stuff like a crack or porosity or amorphous phases. And so once we've grouped those together, then we can start thinking about size and shape and morphology measurements. So this is just an example from a CAD-TEL solar cell where there's quite a bit of porosity after a treatment step. So we can go in and say, well, show me what the pore sizes are, measure that, compare that to the grain size, and as they tweak the different treatment steps to get an idea of pore size and pore distribution as a function of processing. And then we talk about saving all these patterns for reindexing, for Prius, for NPAR. One of the things we've put in is what we call HDF5 support, which is a file format container that allows for easier handling of these files within Windows and makes it easier to move data around. It's compatible with things like CrossCort for HR EBSD. It's compatible with things like Dream 3D for 3D analysis. So it's sort of I'm going to say industry type tool or standard that's being developed that OIM analysis is compatible with. So for our final poll, just after hearing these, of clicking which of these you might think would be useful or interesting for your work. I'd like to say there's a prize at the end, but there's not. And the hardest thing about these webinars, just as a side note, is not knowing if people are laughing at your jokes. So I'm on my best behavior. So again, thank you for response. So, to kind of wrap things up into a big picture, there's lots of data, there's lots of features, there's some nice, exciting new features. And it can be applied to all sorts of characterization problems. We've looked at automotive alloys, fatigue and titanium. One of the more novel ones is looking at the evolution of trilobite eyes, solar cells, creep in nuclear materials. But essentially, if something's crystalline, you can start to think about using EBSD to analyze it. There's a lot of applications. It's been really rewarding to watch the growth of these applications over the years. I keep saying things like there's a lot in there, and there is. So one of the things we like to emphasize is some of the training options that are available to help users learn how to take advantage of these features within the software. So, the manual is actually really good. We have step-by-step tutorials, and with OIM 8, those have all been redone to also highlight some new features. There are how-to videos available. There are training courses available. There's on-site training available. We have Ask the Expert web sessions where basically you can call in and ask questions, and we try to address them. And then we have events like this where it's a webinar. This one's a live one. We also have on-demand webinars available. So if there are topics you're interested in, feel free to fill those in to let us know. We'd be interested in that feedback because we're interested in providing content that's useful to the market and to users. And so we try to provide lots of different outlets to make that available. So in summary, OIM Analysis provides a comprehensive but easy-to-use toolbox for characterization of this EBSD mapping data. Again, the big takeaway I want is EBSD pattern indexing has been introduced in version 8, brings new capability to really improving your data quality, and it brings things like Kaiscan and NPAR and Prius to the table. And then multi-threading in OIM Analysis 8 allows users to take full advantage of these really modern computers for more efficient analysis. And so we'd also like to point out some of the additional resources that are available. We have a blog at our blog site you can get at from this link or from our website, where a number of us within the organization kind of post our thoughts and ideas on a number of things. We have a bunch of different movies available on our channel on YouTube. We post to LinkedIn and Twitter. We have our webinars, and as always, you can contact us there at info.edax@amatech.com. So with that, I'll conclude the me talking point, and I will at least try to answer a couple of questions here. I'm going to go and try to read a couple. The first one asks, how easy is it to load the patterns into OIM? I've noticed it can take a while to copy the files. So it does depend on what version of acquisition software you're using. With our team software, we now save things in a pattern file, a .pat file, which gives a single file with all the patterns. It makes it easy to copy and load into OIM Analysis. Previously, you dealt with a folder with all the files, and Windows doesn't handle lots of files in a single folder very well when you start talking about thousands of files. So that single file helps a lot, and then the HDF5 format can take all those single files and put them into an HDF5 format as well. So my second question here, and I'm kind of just looking through a list. So it says, how does the interaction volume difference between EDS and EBSD affect Kaiscan? That's a great question. With EDS, the interaction volume is typically larger than it is with EBSD. Probably, we could estimate it by an order of magnitude. And so generally there's almost a spatial shift. If you imagine we're tilted on a 70-degree sample, the EBSD signal kind of comes where the beam first hits the sample, but EDS comes from there, but also comes from a volume sort of below the sample as well. So you can think of it shifted a little bit downward, so that with Kaiscan, if you look at the two, you might see a little bit of shift if your step size is fine enough to see it. So I probably didn't explain it well, but if you're looking at micron, 5 micron steps on large-scale features, it's not going to make much difference. But when you get to sub-micron steps, you'll sometimes see this offset. So what we're able to do to help correct for that is, one, we can just shift the EDS data spatially along the tilt direction to help align things better. The other thing we can do is we can average sort of by different kernels or grains to help use the orientation information to create a bound for the EDS data, which helps improve the differentiation a little bit better. Okay, I have a third question, which is, how does OIM treat pattern background removal? So with OIM Analysis, basically what we're able to do is you can say, I want to use my standard background, or I want to add a different background I've built either using all the patterns or some of the patterns, or I can create a dynamic background or add different image processing. So there's a few different ways you can approach it. Is, one, you can run your software with no background at all and then create different backgrounds for each phase or whatever, or you can start with a basic background and then sort of adapt as you want based on, if one phase doesn't work or the other. I think the most important thing is there's a lot of flexibility built in to address sort of the different challenges that approach, and your best approach kind of depends on your material in that, if you have a material where you're looking at 80-90% is one phase and 10-20% is the other, I may take one approach where if it's more 50-50, I'd take a different, or if it's 30-30-30, I might take a different. It has the flexibility to sort of address all of those. So with that, we've kind of hit the 1 hour mark, and so we don't like to go too much further than that. But if you have submitted a question, you will receive an answer via email. With that, I'd like to thank you for your attention, and we appreciate your time.